Hello everyone, I am Xiaoning Chen, comes from the Institute of Data Science. Today, I want to talk about my own method on predict the concrete compressive strength. Here's my outline. First, I will recap the dataset and show my modify. Then, I will talk about the regression method I use. After that, I will show my experiment settings and result. Finally, I will conclude the experiment what I find. The dataset I use comes from UCI Concrete Compressive Strength dataset. The number of observations are 1030. There are 9 attributes: content of cement, blast, ferrous slag, fly ash, water, superplastical, coarse aggregate, fine aggregate, age, 8 input variables, and concrete compressive strength 1 output variable. And here are the description of variable names. Blast ferrous slag means the mixture of metal dioxide and silicon dioxide. Fly ash means coal combustion product that is composed of the particulates that are driven out of coal fire boiled together with the flue gases. Superplastical means used in making high-strength concrete. Coarse aggregate, fine aggregate means if the aggregate size is more than 4.75 mm, we call coarse aggregate, else we call fine aggregate. The output variable, concrete compressive strength, means the measurement unit of concrete strength. By the way, as I mentioned on milestone, because the value of blast ferrous slag, fly ash, and age are imbalanced, so I bind these 3 variables from 1 to 5, and in method, I will use label encoding to handle binding categorical value. Here is my method. The model of the method can separate to 3 parts: linear regression, machine learning without tree-based method, and machine learning with tree-based method. As for method, testing ratio and data binding, I will do it on different testing ratio, different regression model with and without data binding to find which combination can get the best performance. The following 12 items are the model I use. First, I will demonstrate the linear regression and its variant model, like linear regression, lasso regression, ridge regression, and elastic net regression. Then I will demonstrate machine learning method without tree-based method, like KNN, MLP, and SVM regression. Last but not least, I will demonstrate tree-based method, like decision tree, like GBM, XGBoost, CatBoost, and random forest regression. Okay, let's start the linear regression and its variance method. By the way, the method with star text means this method has been used in related works, which I refer from related works. I set the test size from 140, 240s to 2040s. The left of the plot are the RMSE on 4 linear regression method. The right of the plot are the R-squared score on 4 linear regression method. In this case, I don't use data binding. We can see that we get almost same of RMSE and R2 score on 4 models. How about dataset with data binding? The upper 2 plots are the performance with data binding in 15% of testing ratio. We can see that the RMSE decreased from 9.6 to 7.7. R-squared score increased from 0.65 to 0.75. It is a good improve. Besides, in linear regression method, we can see that the lasso regression can have the best performance of the 4 models. The following group bar chart are the coefficient of 4 linear regression models with data binding. Although fly ash have been bind from 1 to 5, the coefficient of fly ash is still very small. Maybe in this case, the importance of fly ash are low. The following group bar chart are the coefficient of 4 linear regression models without data binding. Since we see that the RMSE and R2 score are almost same in previous plot, so we can see that the coefficient of 4 linear regression models are almost same. The following plot are the coordinate with predicted value and the true value. Compare with without buying data. We can see that the former plot fits x equals to y better than the later one. So, does it mean that data binding can improve the performance? Let's see machine learning method. The upper two plots are the result with data binding. Unfortunately, the performance cannot improve in this for machine learning method. In 15% of testing ratio on KN regression, we can see that the RMSE increased from 6 to 8.2. R2 score decreased from 0.75 to 0.55. Besides, machine learning model without tree-based method shows worse performance than linear model. The following plot are the coordinate with predicted value and truth value. Compared with without binding data, we can see that the former plot fits x equals to y worse than the later one. How about tree-based method? Because I want to make the plot 4x4, I mentioned the decision tree before. The upper two plots are the result with data binding. Likewise, the performance cannot improve in this for machine learning method. In 15% of testing ratio on random forest regression, we can see that the RMSE increased from 5 to 6. R-squared score decreased from 0.9 to 0.86. But there are something different with other machine learning model is that the tree-based method show better performance than linear model. Besides, it is surprising to me that XGBoost get lower than 4 RMSE and the 0.95 of the R2 score. The range of the output variable are from 2 to 82. It is mean that the XGBoost in 15% of testing ratio get only 5% or less of error. The following plot are the coordinate with predicted value and the truth value. Compared with without binding data, we can see that the former plot fits x equals to y worse than the later one. The following group bar chart are the importance of different variables of tree-based method with data binding. Similar with the coefficient of linear model, the fly ash variable is also not important compared with other variables. In contrast, we can see that variable Simon and H play an important role on this data set. The following group bar chart are the importance of different variables of tree-based method without data binding. Through this performance get better than the former. The importance of each variable are similar with the former one. The last part is the conclusion. First, we get a better performance when the missing ratio is from 0.05 to 0.2. To make the intersection of maximize the missing ratio and get a better performance, I choose 15% of data to testing. That's why I plot all of the figure with 15% of testing. Then, in linear regression and its variant, data binding can improve performance. In contrast, in machine learning or tree-based method, data binding cannot improve performance. After that, as the testing ratio grows, the RMSE without data binding increases rapidly than the dataset with data binding in tree-based method. Last but not least, I can conclude that tree-based method get the best of the performance of three parts. Among all, XGBoost gets the lowest RMSE and the highest R2 score of all. The rest of the part is my reference. This is the end of my presentation. Thank you.